Hello, everybody. Thanks, Agnès, for accepting our invitation to be here today. Agnès is a project scientist at LAC KIPAC since 2022. She got her PhD at the Institut d'Astrophysique Spatiale in Orsay, working on SIMBI polarization and early universe. Then she got a postdoc position at the Royal Observatory in Edinburgh, and then at JPL, working on galaxy survey, cosmology, and tests of gravity. And today she will present weak lensing cosmology and tests of gravity, tensions, and prospects. Agnès, you can start, please, when you're ready.
Thank you, and thank you everyone for joining. So I will talk about weak lensing cosmology and test of gravity, and I will highlight specifically tensions, as this is the CosmoVerse seminars. Okay, so to start with, we have our legacy from the past century of cosmology. Is a standard model of cosmology, the ΛCDM model, where the universe has been expanding since the Big Bang, and we believe during cosmic inflation, the fluctuation of matter got created and then grew to become the large-scale structures that we see in the universe today. And I think in the past decades, one of the big results was the cosmological result from the Planck satellites, measuring the cosmic microwave background temperature and polarization, anisotropy, angular power spectra. And this is what gives us now the most precise measurements of the ΛCDM parameters, where we have mostly dark energy, which is causing cosmic acceleration, mostly dark matter in the matter sector, and 5% of visible matter. And general relativity is our description of gravity. And now, in this coming decade and afterwards, some of the big questions that we are trying to answer are: what is causing cosmic acceleration? What is dark energy? What is dark matter? Did cosmic inflation really happen? What is the mass of neutrinos, etc.? And we're trying to answer this question by probing the recent universe and by measuring also the cosmic microwave background, polarization B modes on large scales. And one way to probe the recent universe is specifically to use galaxy surveys. Because when you image galaxies, we get access to the position of galaxies, which trace the dark matter large-scale structures, as is shown here in this simulation. But also galaxies can be used as background lights, because their lights will be distorted by the large-scale structure, the matter between us and those galaxies, which is the lensing effect. And we use those two effects to statistically probe the matter power spectrum, which I'm showing here an evolution over redshift. And you can see it becomes more and more nonlinear with time. Okay. So one specific measurements that we can do with galaxy survey is cosmic shear. So galaxies are weakly lensed by the large-scale structures on the line of sight. They will perturb the metric, which will deform the geodesics. So the shape of galaxies will appear coherently more elliptical, as is shown here on the left, where we have background galaxies with a mass in between, and we can see the kind of deformation, the coherent deformation that's applied. So to get access to this small signal, which is a percent level signal, we actually statistically measure it over hundreds of millions of galaxies and summarize it in by doing the two-point correlation function of the shape of galaxies. And because we are talking about ellipticities, there are two quantities, so we end up with two different two-point correlation functions. So this is how they're represented, the correlation of the shape of galaxies as a function of their distances on the sky, theta, and we do that in tomographic beams. So for correlating the shape of galaxies in at different redshift. And so in this way, we're directly probing the matter distribution because we are probing the dark matter and the matter on the line of sight. And so there are actually several systematics in cosmic shear. So to fully unlock the information we can get from weak lensing, we often combine cosmic shear with clustering and galaxy-galaxy lensing. So clustering is the correlation of the position of galaxies. So this is probing the matter power spectrum, but with a bias because the galaxies are tracing dark matter with a galaxy bias. So this bias is squared. And in the galaxy-galaxy lensing, we're measuring the tangential shear of background galaxies around lens galaxies in between us and the background galaxies. And here we're probing the matter power spectrum, but with just one factor of the galaxy bias. And by combining those three correlation functions, we get the most out of weak lensing. And we're specifically sensitive to S8, which is this combination of sigma 8, the variance of the density fluctuation in sphere of 8 megaparsecs, and omega m, the energy density of matter. And this is also sensitive to dark energy and gravity. They are very powerful probe of the recent universe. And we often refer to it as 3 by 2 points, so 3 different 2-point correlation function. So because it's such a powerful probe of the matter power spectrum, it has been, weak lensing has been the goal of many experiments. And actually the first cosmic shear measurements were made in 2000. So that's just to remind everyone that's a very recent measurement, but which means it's very exciting because there's so much more to do with it. And this is a plot from Martin Kilbinger's review on cosmic shear, where you see the history of this measurement of S8, which is very interesting because at the time, actually in between cosmic shear measurements, S8 there was a systematic tension in between weak lensing experiment. But right now, in the era of stage 3 surveys, cosmic shear measurements of S8 are pretty consistent in between each other, but they are systematically lower than measurements of the cosmic microwave background from the Planck satellite, which is shown here in blue. And so the survey DES, KIDS, HSC are all ongoing right now and making cosmological analysis using 3 by 2 points to test dark energy, gravity, and to measure S8 with even greater precision. And there is also a lot of development trying to test the different assumptions that goes into our cosmological analysis, like in this DES plus KIDS analysis. But still systematically, S8 is measured to be lower than Planck. And in the coming decades, we will have stage 4 survey who will measure weak lensing with even greater precision because they will look at more sky, more galaxies, and deeper. So on the ground, we will have the Vera Rubin Observatory. So I work for the Rubin Observatory at SLAG, and that will provide the LSST, the Legacy Survey of Space and Time. And then Euclid, which is now in space, will also measure weak lensing, but from space. So we'll have better shape measurements. And then later on, the Roman Space Telescope from NASA will also provide weak lensing measurements. So I'm especially interested in challenging general relativity on cosmic scale with weak lensing. So why do we want to do that? So first of all, it can be an explanation for cosmic acceleration. So either cosmic acceleration is explained by a dark energy, which we have to understand what it is on a microscopic level. And an alternative is to say that GR is not verified on cosmic scale. Another question could a modification to GR explain the S8 tension? And also, in general, I think, to me, one thing that's very exciting is that we can start to test GR more and more precisely on cosmological scales, because it's tested very well on local astrophysical scales. So I think it's great that we're going to try to have the full picture of general relativity. And there are many ways to modify GR, which is represented here on these slides. There are many ways that we can test the modification to GR. And the universe is a great laboratory to test gravity, because gravity is the main force at work on those scales. It impacts the evolution of matter distribution and the path of light in weak lensing, for instance. So cosmology offers a unique test of gravity in a regime different from gravitational waves. So this is here on the bottom, a simulation of the matter distribution in general relativity and in modified gravity, in the F of R gravity on the right from this paper, and where we see how the small scale structures are changed in modified gravity. But I'm actually especially interested in testing gravity through metric perturbations. And the idea here is to directly ask, are modification to the potential that's causing weak lensing and clustering as expected as in GR? And we do that often by modifying the Poisson equations by this parameter sigma naught. So this parameter tells us about how the geodesics are modified. So it directly impacts cosmic shear. Here I'm showing an example of cosmic shear for different values of sigma naught, and we see that a higher value of sigma naught means stronger gravity, so higher, greater amplitudes of cosmic shear. And because there are two potentials that are deforming the metric, we also have this second parameter, mu naught, which modifies the dynamic. So the way matter reacts to gravity. And both sigma naught and mu naught equal to 0 corresponds to GR. I find this especially interesting because actually in modified gravity, we generally change the dynamics, but not necessarily the geodesics. So here with sigma naught, we're directly testing lensing, if weak lensing is as expected as in GR. And there are complementary observables to weak lensing. With redshift space distortion, we probe the way matter, the growth of matter structures. This is showing F, so the growth rate times sigma 8 from this redshift space distortion measurements as a function of redshift and for different values of mu. So we see here how mu, we're sensitive to mu in F sigma 8. And of course, the cosmic microwave background, temperature and polarization power spectra are sensitive to sigma and mu through the ISW effect and through the lensing of the CMB. So to kind of summarize the status of sigma naught measurements, there were some of the first sigma naught measurements with CFHT lens, which was bang on 0, so very consistent with GR. And then in one of my papers, we reanalyzed CFHT lens, but updated RSD measurements and CMB measurements using Planck. And we also used measurement from the sense verification data from DES, which were not as good as CFHT lens, of course, but then that was the first step to then go to the DES first year of observation. Okay, so now of course, I wanted to measure sigma naught with the newest data from the dark energy survey. So with Jesse Muir, we formed and co-led the DES extensions team with all these great early career scientists and professors and postdocs. And we considered different, including Eleonora, by the way, and we considered different extension to ΛCDM. And here are the results here on the right of a dynamical dark energy, which is one of the tests that we want to do to understand, is dark energy constant with time? Is it the cosmological constant, or is it varying with time? We also tested for a non-zero spatial curvature for sterile neutrinos and for measurement of sigma 8 in redshift bins. And we did sigma mu tests of gravity. So to do these tests, we take a Bayesian analysis, as we do, as it's quite standard to do in cosmological analysis, where we sampled the likelihood. And we actually we had a whole effort in the dark energy survey to validate the use of the polychord sampler to sample the likelihood. So here we estimated the preferred parameters by comparing the data to our model. So as is shown here, we sample the likelihood until we cover the full posterior. And this validation of the polychord sampler is detailed here in this paper. So we have the ΛCDM model with all the nuisance parameter for the dark energy survey measurements of 3/2 points, and we add these extended parameters like sigma mu. And what I think is one of our strengths to do this as a big team is that we can test for the impact of many systematics, and to make sure that if we detect something, any deviation from beyond ΛCDM, it is not due to unknown systematics. But to do that, that means that we have to run many chains, many MCMCs. So we run more than 700 of them. So the data that we use to do this test was 3 years of observation from the dark energy survey, because they are so unique. There's the largest shape catalog to date, so 100 million galaxies that were used to measure weak gravitational lensing. And here is on the top right is the cosmic shear measurement. And the lens galaxies were optimized for the dark energy equation of states, and were using 4 redshift bins. So in ΛCDM, in the dark energy survey, which mapped 10% of the sky, we obtain a cosmology with 4% precision, which is shown here on the bottom right in purple, compared to the result from Planck satellites in blue, in the sigma 8 omega m plane. And most of our work in this extension analysis team is actually to ensure the accurate modeling of the data vector in extended model. So for sigma mu, one of the first things to do was to propagate the effect of sigma mu on the lensing potential and the matter power spectra into weak lensing and clustering. To do so, we used MGCamp, and we also had to modify the way weak lensing was theoretically computed. We also have to ensure a consistent modeling of intrinsic alignment, galaxy bias, and other observational effects. And I actually have shown in one of my papers that the intrinsic alignment has the biggest impact on sigma naught. So I think it's something that we'll have to develop in the future to ensure that we have description of intrinsic alignments in modified gravity. But for now, in DSCR3, we just use the standard nonlinear alignment model with redshift dependence. We also take the approach to remove data points on scales that we can't model very well. So that specifically means in sigma mu to remove scales where first, we don't know where the bionit feedback has an impact. So that is in ΛCDM, we remove those scales. But in addition, we also remove scales where the nonlinear power spectrum, where the power spectrum becomes too nonlinear because we don't have a good description of it for sigma mu. And again, this analysis is validated against systematics, and it's blinded at the level of the parameters. So we never look at the result on sigma naught and mu naught until we were sure that we weren't going to be biased because of some effects from a mismodeling or systematic effects. So to talk a bit more about the nonlinear scale cuts. So the nonlinear evolution of matter distribution, so the nonlinear power spectrum is usually described using n-body simulation in ΛCDM. And people have been working on it, but we still don't have a clear description for sigma mu. So our approach, which is similar to what the Planck 2018 did, is to remove the nonlinear scales by ensuring that the delta chi-square between a nonlinear data vector and a linear data vector is below 1. So so that means in the end, we just keep 255 data points from 462 data points used in the ΛCDM analysis. So that's a huge loss, but we had to do it to be fully robust. So this is our results in blue from DES alone. So the main takeaway here was that DSCR3 3x2 points is consistent with GR. Within 2 sigma, sigma naught is 0 and mu naught is 0. So our chain are available at this link. And so feel free to use them in your papers. And they are all explained in this paper. So here I'm completing this sigma naught measurement, this history of sigma naught measurements by adding DSCR3. And this is combining with RSD and CMB to pin down mu naught and sigma 8. And the other takeaway for me is that there seems to be a tension between Planck and GR, but also Planck and 3x2 points. So looking into the sigma naught S8 plane, we see here the contours in red are from Planck alone. So that's the temperature and polarization angular power spectra with no CMB lensing. And in blue from the 3x2 points from DES. And we see that there seems to be, they are not fully overlapping, which is very intriguing. And we think it's caused by this fact that the polarization and temperature power spectra are lensed. The lensing of this power spectra is not consistent with the lensing we get from the 4-point correlation function of the polarization. And this is summarized in this parameter A lens. So this is taken from the Planck paper showing sigma naught and AL with basically the data that we use on the left is in black here. So we see here that Planck is, in this case, more consistent with sigma naught of 0. But still, this is something we're digging into because I think it's very interesting. So are any of our beyond lambda CDM model a solution to the S8 tension? So in our paper, we have this plot where we show S8 measurements from Planck in red and from DS in blue for the different models, but also for the different modeling choices in lambda CDM. So for sigma mu, I think for now it's we can't really tell, mostly because we had to remove so many scales. We lose a lot of constraining power, so it's hard to say anything on S8. But we see that lambda CDM plus this A-lens parameter kind of resolve this tension. So here on the right, I'm showing how using all the nonlinear scales on sigma mu would help increase the constraining power indeed. So I think that's something we have to do in the future to do this type of test. So we are also working on further tests of gravity, looking at different sigma mu parameterization because they're actually functions of time and scale, and looking at actual modified gravity theories like F of R or the dilaton or symmetron models, which are fifth force kind of models. And so right now, because of the modeling constraints that we have, we won't be able to say anything about the sigma 8 tension using these modified gravity models, I think. We still have to see for F of R, but for the dilaton and symmetron, I don't think we did say much. Okay, now I want to highlight the use of CMB lensing to test gravity. So the cosmic microwave background is lensed by large-scale structures, and that means it's also sensitive to sigma naught. And this is showing here on the right, the power spectrum of the lensing potential for different values of sigma naught. So you see how the amplitude and the peak is shifting. So the Planck satellites did great measurement of the lensing. This is actually a map of the lensing potential, the integrated lensing potential. And today and in the future, we're going to get more and more precise measurements of CMB lensing. So recently, the ACT collaboration released their cosmological results from ACT with 43 sigma measurement of the CMB lensing. This is showing a plot from their paper comparing ACT with Planck and DS and other weak lensing surveys. So with my student, David Zingelewski, over the summer, we wanted to use this data to test for sigma mu. So here reproduced the results from ACT using Cosmosis, so our cosmological inference code. And we also did this same nonlinear scale cuts approach, which means removing 2 data points. So this is very preliminary results that he obtained, and where we see sigma naught is very high from just ACT lensing alone. And we believe that's driven by specifically one data point, but we're still working on it. This is in preparation. And when combined with other datasets like RSD from EBOS or SDSS in general, sigma naught goes back to 0. So the future of test of gravity is very exciting with CMB, because a lot of CMB experiments want to measure the B modes, but they will also increase the lensing measurements. And in parallel, we have also galaxy surveys like LSST, Euclid, Roman. And I actually updated my forecast from LSST year 10 on sigma mu, and this is what I obtained, where you see the improvement from DSCR 3 to what is expected from 3x2 point from LSST, the full survey, the full 10-year survey. So that's very, very exciting, but that means we also have to progress on the modeling side. Okay, I'm gonna now talk about a different but related topic, is that with these coming surveys, we'll have a greater volume of data, and we'll want to test a lot of theories and a lot of models. And right now, at the moment, I feel like there are only a few models that are preferred by the community, and tools are developed to model these the cosmological observables in these models. Like F/V gravity, for instance, is very well studied. And this is mainly from theoretical motivations, which is, I think, is great. But I also want to convey that we can compare models at the level of observables. So the idea here is to say, like, do we need to test that many models, or do they have the same impact on 3x2 points, for instance? So to answer this question, we can, so in this paper, we propose to use self-organizing map to answer this question, but we can use any other dimensionality reduction algorithm. And that would help tell us if we need to look at a specific theories, or if two theories have the same impact or not. So how would that work? So first, you would need to produce a training set. So what I did was to fix the cosmology, because we only care about knowing, for instance, does modified gravity have a different impact than, for instance, varying sigma 8? So I consider different cases, different modified gravity models, and I vary their parameter in each cases. And I also have a case where I just vary sigma 8 and produce cosmic shear theoretical predictions. So in this case, just angular power spectra. So we have, so we end up with this kind of data. Okay, and so now this is our training set, and the next step is to train the self-organizing map. We use this SumPy algorithm, and this is the self-organizing map that we end up with. So what does this mean? So this is something I've done specifically for this talk. Actually, this is not from the paper, but I think it's very interesting. So what is this saying? So each pixel of the self-organizing map corresponds to different models that basically have the same impact on 3x on cosmic shear, just cosmic shear. And their colors corresponds to the number of models in each pixel. And you can also kind of color the map by just one parameter, for instance. So I want to ask, where do the cosmic shear power spectra varying sigma 8 ended up on this self-organizing map? And this is the answer. They ended up around here. Okay, but now what about sigma naught? So the power spectra varying sigma naught and end up in this top right corner of the self-organizing map. And that means that sigma naught has quite a different impact from a sigma 8 because they don't really, I mean, they overlap a bit, but actually mostly the self-organizing map is able to differentiate between them. So that's probably indicating that sigma knots won't be able to fully solve the sigma 8 tension because it has a different impact on cosmic shear. Okay, I'm just gonna end with a few slides about something I would like to develop more, but I just didn't have time or support to do it. But this might be a good forum to do it because it is very relevant for tensions. So in the future, we'll have many cosmology coming from many surveys, galaxy surveys or CMB experiments. And right now, each survey, they publish their analysis in a paper. And in general, it's like at least 30 pages and probably in average, probably like 50 pages. So the number of time, for instance, I open the Planck paper and scroll down to find the table with the measurements or like the plots, that will only get worse with time, especially as each survey will have different cosmological analysis as well, like from year 1, year 5, year 10, whatever. So how can we help us like summarize the results? So first of all, just to say, I think a table of contents in papers is that's a huge step that helps a lot. But maybe we can have a tool to centralize results. So I have a prototype here at this link where like the idea is that I made plots from public chains using different, like for instance, that was with DSER1 and Planck 2015, and like overplotting them. And then there's a HTML page that shows this plot based on the selection you make. So for instance, if you just want to show DS, you just say yes to DS and no to Planck, and it will only show DS results. And you can also choose the parameters that you want to show. So this is just a prototype just for this case. But I think it would be super valuable to have that for like current cosmological analysis so that we can quickly see, okay, what does this experiment says on sigma 8 or H naught or whatever. And we have everything on one page. Okay, so I'll end up here. So to summarize, the results from the quick lensing and clustering from the dark energy survey, 3 years of observation, are consistent with GR, but we see maybe a tension between Planck and DES in sigma mu. We are also working on CMB lensing constraints on sigma naught. And one of our next challenge, I think, if we want to answer this big question of like, is a modification to GR needed to explain cosmic acceleration, we have to develop accurate modeling of our observables in beyond lambda CDM. I also showed a use of a machine learning algorithm like self-organizing map to do theory exploration and showing that maybe sigma naught might not be a solution to the sigma 8 tension. And again, highlighting that there is a rich synergy between cosmological surveys in the 2020s, like in test of gravity, and that if, I'll end by saying if you want to help on this tool or if you find it interested, then I'm very happy to discuss more. So yeah, I think it's a very exciting time for this kind of studies, and but we still have a lot of work to do, I think. Thank you.
Thank you so much. Thank you for the very nice talk. Do you have any questions?
Yeah, thanks a lot for the talk. It was very interesting, and I particularly like the attempt of exploring all the models. Could you maybe go back to the slide 29, since I would like to understand the self-organizing maps a bit better? Okay, so here you say, okay, you vary the parameters for the modified gravity. So are these theory-specific parameters for each modified gravity theory, or are these like effective theory parameters that comprise a lot of theories?
Yes, so you could choose either, but in this case I just chose so f over gravity, so varying just the FR0 parameter, and I also use these dilaton and symmetron models, which also are parameterized by one parameter. But that would be very interesting as well, is to take something like like Hondesky parameters and see how they map onto f of r or sigma mu or S8 even. Yeah.
Okay. And then so how do these? So it seems like you're still doing the analysis for each kind of theory individually, right? So I don't quite understand how the self-organizing maps can reduce. I mean, you want to reduce the computational power at the end, right? Or the computational.
Yes. So so the goal here exactly. It's I don't think. I mean, maybe there are ways to use that to not go to this step of parameter estimation. But to me, the most interesting is to actually just use it as a way to choose which model to look at, given some sensitivity of your measurements. Because maybe when we look at, dynamical dark energy, sigma mu, etc., maybe for like a specific measurement and covariance, maybe it has the same impact on 3x2 point, and then you don't need to actually analyze both cases. And when we produce the training sets, you can fix the cosmology, so you just have to vary one parameter. So that's not that much computing power comparing to doing like a MCMC, for instance.
Okay, thanks.
Thank you very much for your talk. I am quite excited and impressed, and thank you very much. I have a more curious question first, that is, if when you talked about the MGCamp used with that validation of cosmoses and polychord, if this modification is available, or is something like only for you and collaboration?
Yes.
Like the kind of modifications you have done in the MGCamp.
Yes. Yeah, so actually, in MGCamp right now, okay, so first of all, there is a later version of MGCamp. We use the version that's from before. And there is sigma mu. Okay, so maybe just... so when I'm showing this, when I show these equations, I'm actually simplifying, because sigma and mu can be any functions of time and scale that you want. But here I'm just showing this parameterization with omega lambda, because that's what we chose to do in DES. And I must say, actually, I didn't say that, but kids, for instance, did also test of sigma mu, but using a different approach, like just measuring sigma and mu in redshift bins. But anyway, and so I believe this parameterization is in MGCamp by default, but the modification, and but I don't think MGCamp is in the... So there is an older version of MGCamp in the public Cosmoses. So I don't think the newest one, or the one that we use for this case, is in Cosmoses. And the value potential modification are in Cosmosis, but not for the intrinsic alignment. I think so that's a limitation. But it will be soon, but I'm still working on it because I'm adding this other parameterization. So sigma mu that depends on time and scale, and also going as the scale factor to the power of S, where S is any number you want. Yeah, so I think we'll release everything once we're done with this paper.
Okay, very good. And the other question is about also here in this part about the okay, you said that you have done something about propagation of the via and multiple spectra to this 3 to point thing, and I would like to ask how important is higher order corrections for the lensing, for example, in the vial, because I know some works of Giuseppe Fanizza and Giovanni Marozzi that they consider higher orders for example, the post-born approximation. So they consider higher orders to the vial, and if this is something that has some important impact on the sigma naught, mu naught.
Yeah. Okay. So basically, we use validations in lambda CDM. So if some assumptions are made in lambda CDM that we keep and we verify, but this is our baseline. So like the post-born like modifications we didn't add, but that could be something. Yeah, that could be something interesting to look at. Yeah. This is large scale effects, right?
Yes.
Yeah. And because we are using the largest scales for sigma mu, but I think it's very, very large scales. So yeah, that's interesting point. Yeah. Maybe worth looking into. Yeah.
Oh, okay. Thank you. Thank you very much.
Thank you.
So let's thank Agnès again. Thank you so much.
Thanks a lot.